speaker for today is Professor Zuleima Karpyn. Professor Karpyn is the Donohoe Family Professor of Petroleum and Natural Gas Engineering and Associate Dean for Graduate Education and Research in the College of Earth and Mineral Sciences at the Pennsylvania State University. Her research examines rock and fluid interactions and how those affect storage, trapping, and displacement of gases and liquids in the subsurface. Areas of application include reservoir characterization and engineering, carbon sequestration, subsurface gas storage, and environmental remediation. Professor Karpyn holds a BS in Chemical Engineering from Universidad Central de Venezuela and an MS and PhD in Petroleum and Natural Gas Engineering from the Pennsylvania State University. Professor Karpyn is a recipient of the 2008 Faculty Earlier Career Development Award granted by the National Science Foundation, the 2010 Wilson Award for Excellence in Teaching, 2018 to 2019 Big Ten Academic Leadership Fellow Fulbright U.S. Scholar both in 2016-17 and 2023-2024, and Distinguished Member of the Society of Petroleum Engineers, 2024. She has also served as Associate Editor of the Society of Petroleum Engineers Journal, Assistant Editor-in-Chief of the Journal of Petroleum Science and Engineering, Associate Editor of Transport in Porous Material from 2018 to present, and Deputy Editor of Geoenergy from 2022 to present. We now welcome Professor Karpyn. Professor Karpyn, the stage is all yours now.
Thank you very much, Neha, for the introduction and for the invitation. Let me try to share my screen and make sure that it all works well. Can you see my presentation slide?
Perfect.
Wonderful. Well, thanks again for the invitation, truly, to ACS Science Talks and be part of this community, be able to present and share some of the work that I've been doing at Penn State University. The presentation that I prepared for this occasion is a collection of experimental observations that were drawn from investigating the unconventional nature of ultra-tight rocks, in particular shales, when it comes to the storage capacity that exists in their pore space. So that's the context for the work that I'll be presenting today. But I wanted to start by giving credit where credit is due. This is a picture of members of my research group. Especially I want to give credit to two former members of the research group, Xuanxin Liu and Nirju Chakraborty, because they are really the force behind the work that I'm presenting today and the primary authors for these findings and publications that followed. In terms of the motivation of this work, why shales? So shales are these fine-grained sedimentary rocks that have formed through the compaction and cementation of clay and other silt-sized mineral particles. As you can see in this map, these shale deposits or formations are widely available worldwide. At the same time, access to natural gas production from these formations offers a low carbon energy alternative to other fossil fuels. In particular for the US, that has been, a significant impact on the a transformational change in the global market in the participation of the United States through what we call the U.S. shale revolution that peaked between 2015 and 2019. So this is an important source when it comes to storage, transport, and understanding those mechanisms for shales. It has implications, important implications in the oil and gas industry, but at the same time, because of the characterization required to produce hydrocarbon resources from these deposits and understand these systems, we are at a point where there are certain attributes that make shales an interesting storage alternative in the subsurface for things like CO2, potentially hydrogen. So, for example, they have a proven storage integrity. They're better geological seals than conventional reservoirs. And like I started, this slide is this abundance around the world, make them potentially attractive for other things other than extraction of hydrocarbons. When we're considering depleted gas reservoirs, those can become potentials for interesting storage alternatives. So that's pretty much the context for the discussion. When we think about gas storage, we think that the total amount of gas stored inside a rock within the spores material. Part of that gas resides as a free phase. Part of that gas can be adsorbed into the surface of the solid rock. Part of the gas can be dissolved in a coexisting liquid phase. For the sake of this presentation, I'm not going to consider gas dissolution into a liquid phase because these experiments have all been single phase gas. For the case of conventional rocks that have larger grains, typically sandstones, the gas molecules, or in these systems, the gas is largely residing or stored as a free phase. So the pore volume provides the space for that gas to exist and reside and be part of this system. As pores get smaller in other types of formations, all the way going to things like shales on the kind of on the right-hand side of the spectrum, complexity begins to grow because as pores get smaller, the gas molecules are forced to interact more with the solid walls. Um, Additional also complexity in terms of the chemical composition of the rock material itself, or whether we have organic rich lithotypes, that can also add complexity to the nature of the kind of the storage type portfolio. So having gas adsorbed into the solid surface or interacting with the solid surface becomes more relevant. There's also a growing body of evidence that thermodynamic properties of gases are altered by extreme confinement in pore spaces like this. So that creates also an interesting condition for us to be able to assess storage capacity. And the dominance of these nanoscale porosities in shale, this range of 25 nanometer, this kind of right-hand side of the imaging that I'm presenting, creates challenging in our predictive ability to effectively assess a storage capacity. And on top of all of that, there's a limited experimental evidence or measurements of in situ fluid properties for gases taken up at these nanopore shales. So that presents the need and the void that this work hopes to contribute to, and it consists on the experimental investigation of gas storage capacity in ultra-tight rocks. We've divided this work into three segments. One objective first that attempts to address storage capacity, measuring the storage capacity of different types of gases in low permeability rocks and a variety of them. A second portion, which is an attempt to look at a spatial mapping of that storage capacity. Where is the gas being residing within the entire rock, and proposing a practical approach to quantify that spatial distribution through measurements of concentration or density within rock cores. And finally, the last component is once we look at storage capacity and quantify, once we identify this spatial mapping of that storage. So the last question is what controls that spatial mapping, what controls the degree of storage capacity that we see in different combinations of gases and rocks, and being able to investigate that relationship between the gas storage characteristics and physical or compositional properties of the rock to be able to attribute cause to these variations. The methodology that we followed, experimental methodology started with a traditional porosimetry, a pressure decline porosimetry. We have, and the intent is to obtain first a baseline measurement of pore volume or the porosity of the rock. We have here a core sample inside a sealed container. The samples that we utilize approximately were 12 millimeters in diameter, 30 millimeters in length. And we connect this system to a source of gas and initiate a pulse of helium. In the initial conditions, we use helium to estimate, porosity, baseline porosity, and the pore volume. So we introduce this pulse of helium, close the system, and allow pressure to equilibrate. Pressure will be going down as helium penetrates more and more of the pore space within the rock. And that final equilibrium pressure will serve as an indication of what the available pore space is within the rock. And we use that as our measurement of a porosity. With that, we're able to construct a plot for these four different shale samples that we use. These are four U.S. samples from four U.S. Shale formations: the Bakken Formation, Marcellus, Haynesville, and Mancos. And we did this pressure decline porosimetry test with helium as a baseline, and then with methane, argon, and later on we did also ethylene, at least for one of them. What we find in terms of porosity measurements, they're ranging between 5% for Mancos, 16.4 percent for Haynesville. It has a larger porosity. This particular Haynesville sample, I remember it being still a shale, but maybe borderlining with a tight sand as well. Then when we perform the exact same pressure decline test with methane, we were very surprised to identify what came up as an equivalent measurement of porosity or equivalent measurement of gas uptake by these samples. What this reveals is significant excess of gas, in this case methane, being able to penetrate the rock. This was very surprising for us. Methane is a larger molecule than helium, so it was difficult. We'd not be able to justify this excess uptake just by just the nature of the pore space available for the rock. We did that with argon, and we observed similar results. We see that in the case of Marcellus, and what we see the greatest jump in this excess intake of gas for these samples. So this is something that we observed consistently. We tried a couple of times, and we wanted to explore a little bit more deeply. When we look at that excess uptake of gases and we take a closer look at it, this is what we observe. This is just the proportion of the excess gas uptake in addition to what we can attribute directly to pore volume available for occupying the gas as a free phase. We see that the uptake of different gases exceeded definitely the storage capacity that we can attribute to pore volume alone. The helium pore volumes that we saw before are certainly not representative of the true storage capacity that these four different cores had for these different gases. And the excess gas storage that we are identifying here by these bars is quite significant. It is not it's not something that can be ignored. And more than 40% of the total gas in place is residing in most cases as this excess uptake. At the same time, every pairing of gas and shale seems to have a unique storage behavior. So at this point, what we've seen or looked at is this, surprising result of the potential ability of these ultra-tight rocks to accept gas stored in addition to a free gas phase to a significant degree. We even tried ethylene, and the amount was even more for ethylene being an even heavier molecule. So this called for closer examination. And the next element that we incorporated into this experimental work is to incorporate X-ray CT imaging. It's X-ray, microtomography. It's a core element of the research group. In the picture, you saw it in the background at the beginning of my presentation, where we try to examine in 3D, create digital replicas of rock samples. And in this case, we've used it to try to monitor the a concentration of gas penetrating this rock sample. For this type of analysis, we have to use in a radio opaque gas. So helium or methane would not work for this type of testing for it to be visualized using X-ray tomography. So as a probe gas, we use pure xenon, and we were able to conduct a similar, the identical, in fact, um, pressure decline experiment, but in situ in the scanner using xenon for the same back in Marcellus and Haynesville shale cores. We're able to scan the sample at initial, we call dry conditions, and then after the equilibration, after that pulse of xenon equilibrates and pressure goes down, we're able to take another volume image of the sample. Here's a display of what it looks like, and we're gonna try and see if the video works. So this is the Haynesville shale core. You can see some of the details in it, some of the grains, some micro cracks, a little bit of a chunk missing. We then introduce xenon into the sample. And this color that you see shows the arrival of xenon. Because these are digital data, we can remove portions of the data set, remove the rock, look at the distribution of X-ray attenuations attributed to the presence of xenon. And then after we look at the equilibration, the final equilibrated state is shown here. And this allows us to then look at the attenuation of X-rays attributed to the presence of xenon, and we use that as a basis to do a spatial mapping of densities, or in this case, as, would be somewhat equivalent or analog to concentration. So, so this is what we did. I'm providing the reference for the detailed work here at the bottom of the slide. I won't dwell too much on what the treatment was, but in general terms, what I'd like to say. So we were able to make these measurements of in situ fluid density, in particular, in this case, is xenon, in multiple shale cores, where we use a simplified attenuation equation where mu is the X-ray attenuation, the density is the density of the substance of the material that we're scanning, that Z is the effective atomic number, A and B are constants that account for photoelectric and Compton scatter proportionalities that can be obtained for the type of scanning conditions that we have. And with that and the notion of what the porosity distribution is in space for these samples at every particular voxel location, we can combine these two equations and be able to estimate or calculate the density of xenon, the fluid that's occupying the pore space at equilibrium conditions. We can estimate that for every voxel location from a notion of change from the attenuation from dry conditions to equilibrium conditions, but also normalized or taken into account or relative to the porosity that exists at that particular location. So this was, really powerful, being able to have this spatial mapping of xenon densities estimated from CT imaging. And here at the bottom, what I'm representing is sort of this idea that we have a dry scan where we see the rock, the pore space. Once we introduce a fluid, in this case xenon, and reach an equilibrium image, we can do an image subtraction of those two states and obtain the attenuation attributed to the fluid alone. And that attenuation attributed to the fluid alone relative to the porosity that exists at that location allows us to compute density. And that's exactly what we did. So this is a representation here of in situ xenon density distributions. On the right-hand side, you see rectangular volume region of interest or section from the three cores that we scan under similar experimental conditions for the Bakken, for the Haynesville, and the Marcellus. And then at the same time that we did, these are histograms of density distributions for every location that we find in these volumes of interest. For reference, I think it's important to mention that the density of xenon at equilibrium conditions, as a free gas, is 127 kilograms per a cubic meter. So 127 is somewhere here. So we see here a demonstration of a degree of densification of that xenon with different types of rocks. For the Bakken core sample to a lesser degree, a greater level of xenon densification in the pore space for Haynesville, and an even greater one for Marcellus. So this is completely consistent with the pressure decline porosimetry measurements that we saw before, where we can see again that there's a much higher I think manifestation of gas uptake for the Marcellus, but also to some degree for Haynesville and Bakken. So we see also an evidence of localized phase intensification, because we see here, for example, for the Bakken, some spots are blue, some are warmer colors, indicating that there's a spatial difference to where that densification is occurring. And this provides really an interesting or a suitable pathway for us to go into the next question, which is the attribution of cause. Is this is can we attribute this to the nature of the rock itself, material composition, structure? What is causing this effect of densification at different degrees for different rocks, and also with location within the same rock? So that's what we're presenting here in simple terms. Here at the bottom, I brought this same data that I presented earlier in my slides deck, where this is the excess methane, in this case, the excess methane uptake across different rock samples. And we see that the Marcellus shows the one that shows this most salient increase in this excess uptake, followed by Haynesville and Mancos, and then ultimately the Bakken rock. They're labels as 1, 2, 3, 4, the sample number, and that's how they're mapped in this ternary diagram to indicate kind of the proportionality of these different minerals. So what we see here is that so, for example, the Marcellus shale shows a significantly higher excess of methane that we could not attribute to just pore volume relative to Bakken. But when we see here in terms of the compositional properties, those are not very different in terms of the clay content, quartz, or carbonates, and similar. And in the cases where there's some differentiation, so for example, there's much more quartz for the Marcellus, Bakken, and Mancos than probably for the Haynesville. That doesn't seem to provide us with a justification for the trends that we observe. So this rock composition, we did not find in our experiments a correlation between rock composition and this attribution of storage capacity. We also looked at total organic content. And in this TOC analysis, what we see here is that the organic content of these Marcellus, Haynesville, Mancos, they're not very different from each other, definitely more than Bakken, but still, relatively low, and the trend doesn't justify the differences that we see. So for example, we would think that perhaps a higher organic content could be associated with um, a larger intake of methane. But that was not the case. The Marcellus Shale is the one that has the highest excess methane uptake, but it is not indicator here of the same quality in terms of organic content. So our conclusion from this collection of evidence is that the composition does not appear to be a very good indicator of the observed storage behavior. Then, then we proceeded to look at more structural properties. We created these pore size distribution approximated pore size distribution plots for Bakken, Haynesville, and Marcellus. In there here, Bakken, Haynesville, and Marcellus in that sort of an order of degree of densification or uptake, less for the Bakken and much more for Marcellus. These were obtained, these measurements were estimated from scanning electron microscopy, obtain at different windows of observation to try to observe some of the smaller pores and measure them and some of the larger pores. And what we see here is that for the Bakken sample, the pore size distribution, it ranges from zero point 0.1 to 10, 10, 20 microns in size. In the case of Haynesville, we'd look at smaller pores, less than 10 microns. So definitely, smaller pores than what we see in the back end. But for Marcellus, there's an order of magnitude smaller and a, significant, proportion of the um, pores, ranging from 0.01 to zero point 0.1 microns in size. So definitely a correlation that we see here in terms of the pore size distribution or the pore size range or characteristic pore size in a sense with that degree of densification or additional receptivity or capturing these gas molecules in place. We also looked at pore surface area, especially noticing that pore size had a significant association with the trends that we're observing. Um, I think what's important here with this measurements with these absorption desorption isotherms that give us an indication of surface area, what's important is for the point I'm trying to make is the a specific surface area estimated for these three different cases for Bakken, Haynesville, and Marcellus, with a higher specific surface area of that pore network. In the case of the Marcellus, much less for Haynesville and certainly for Bakken. And again, we see this pattern of correlation with the trends that we have observed in terms of densification. So what we're noticing here is that gas densification seems to be weakly correlated with the compositional properties and total organic content, but pore size and surface area appear to be strongly correlated with the storage capacity because this gas densification is increasing with surface area and decreasing with pore size. And also another point to observe here, some back of the envelope estimates that we did is with these estimates of specific surface area measurements, they also indicate that a monolayer absorbed gas model or concept can only account for 27 to 40% of the excess or potentially adsorbed gas phase, which calls into question this commonly assumed Langmuir monolayer model of absorption as a justification for the additional gas uptake that we're observing experimentally. Here's a summary that exemplifies the same things that I mentioned before. When we looked at the controls on storage, we see, we divide those into compositional properties versus structural properties of the porous material. And we see a much more established correlation between things like specific surface area and mean pore size, because we go here from back into Haynesville to Marcellus, from the cooler colors to the warmer colors, to indicate that degree of densification. And we see that the higher the specific surface area, the more interaction, the more contact exists between the gas molecules, and that and the walls, that enhances this confinement induced densification that we're observing, which is consistent with when we see smaller pore sizes, because again, we're enhancing that interaction between the gas and the solid. So with that, we believe that for these cases that we looked at, this altered gas density that we measure and the storage associated with that was more appropriately attributed to pore structure than to compositional properties of the rock itself. To bring all of this into some bullet point conclusions of what we've observed through this work, is that first, the storage capacity of shales is significantly higher than what we can attribute to porosity. We saw these baseline porosity measurements using helium, very small, molecule, very commonly using in core analysis measurements for obtaining porosity of multiple rock samples. But the ability of these materials to uptake additional mass and associated with that energy as well is significantly higher than what we had assumed originally. The estimated in situ, and this goes to the second conclusion, the estimated in situ gas density is much higher than the free gas density at equilibrium conditions, much higher. So it's quite significant, that effect of densification that we saw for some of these samples. And in terms of the attribution of where do we see this densification effect more pronounced, is when pore size and surface area are stronger correlated. For smaller pore size and larger surface area, we see a strong correlation with that storage capacity. And to extend these conclusions to then, what the implications might be, try to project a little bit more into, what do we do with this, and some of the implications. I'd like to mention that one thing that comes to mind is, this idea that shales, we've already demonstrated that shales can store significantly more mass and therefore more energy per unit volume than expected from free gas models. So that makes these types of rocks, these shales, potentially, promising candidates for long duration subsurface energy storage using things like blended methane hydrogen mixture. So that's something to consider, and I can invite as a thought, as part of this demonstration of findings. The second point here about energy storage capacity is that we demonstrated different degrees of densification with composition and rock type, and therefore different degrees of that would create different degrees of energy storage as well. And in that energy storage will depend again on the type of mixture of a composition and the reservoir conditions, and maybe to some degree one could think that the proportion or the composition of these methane hydrogen blends allow for a tunable energy density when it comes to subsurface storage, because depending on the proportion of hydrogen methane, you could think that you could tune to different degrees of densification. And the last piece here as we would try to kind of integrate, these ideas, is that we need, or there's, at least in my mind, there's a need for some standardized framework to be able to link or translate the geological underground storage volume kind of assessment into equivalent electrical energy units. It's something that could be of significant use if we obtain a really good understanding of how to quantify how much we can effectively store volumetrically in terms of that density is attributed to the conditions that we have in these rocks. Then we would need sort of this framework for linking the two, or the translation of volumetric geological units to electrical energy units at the surface level. So quantifying that storage capacity under relevant conditions and developing this framework of conversion, then it becomes essential for energy system integration that takes into consideration, the need for underground hydrogen storage. Would be able to then also compare geological storage options with other technologies and potentially position subsurface storage in shales as a viable component of the renewable energy storage portfolio. So that's my summary of the work that we've done, and sort of the proposition, or the kind of the line of impact that I think it connects to. And with that, I would end my presentation, and I, look forward to an opportunity to answer any questions that you might have.
Thank you so much, Dr. Karpin, for the very insightful lecture.